I'm Peter. I'm the chair of this session. Each of our next speakers has a bit under 20 minutes to tell us about artificial intelligence and natural language. The 20 minutes includes question time. We have no time to spare. To save time, I won't introduce the speakers much. Presenters, please introduce yourselves. When you have 5 minutes to go, I'll ring the little bell, hoping that that doesn't interrupt anything. When you have 1 minute to go, I'll stop. Okay, thank you. Philip Wagner, please go
Great.
ahead.
Thanks, Peter. And thanks to Mike and everyone else for organizing this. I'm going to go ahead and share my screen real quick. All right, so there we go. Hope everybody can see that. That's just my RStudio console. It's going to be a little bit of an interactive workshop. So there we go. All right, so let's see. Actually, hold on 1 second. Let me get rid of that. Move that. Okay. Okay, perfect. So, like Peter said, my name is Philip. I'm from the University of Chicago. And so just before we jump into what I wanted to talk about for the day, I wanted to make sure that everybody takes note of the repository here. This is where I've got the code and a couple of data sets, sample data sets, play around with, and you can follow along if you want to. And also make sure if you want to follow along with the TensorFlow and Keras application that you've got Python on your computer, and also make sure you've got the latest version of the Java development kit downloaded if you want to follow along with H2O. Okay, so let's just go ahead and jump in. It's gonna be a little more interactive, a couple of kind of lecture-y type points, just to kind of hit some high points, but we'll work through some code and I'll try to stay in time. Okay, so neural networks and computational research are just meant to build a model. We want to assess and evaluate some kind of a relationship between X and Y, as we might in pretty much any predictive modeling context, but we want to do so in a way that emulates how the human brain is processing information. Okay, so why would we want to do this? Well, it turns out our brains are super efficient, and they're typically pretty accurate, and so too are good neural networks when that are properly constructed in this kind of a context. So indeed, neural networks are super powerful. They've been around for around 60 years or so. They weren't always called neural nets. They used to be called perceptrons. They still kind of are in some circles, kind of depends on who you talk to. But regardless, our goal today is going to be to introduce external machine learning engines, the basics of neural networks, and to then kind of motivate and understand how to properly use and build complex extensions like autoencoders and deep nets and these sorts of things. But to do all of this using external machine learning engines to be able to do this kind of stuff locally, on your laptop, which is just an incredible advance for the field. So really quickly, let's start with external machine learning engines, and we'll talk about APIs, and then we'll talk about neural nets. So essentially, machine learning engines are just kind of massive sets of tools and computational power that include repositories of source code for tons of model frameworks and architectures, far more than any kind of one-off package might be able to kind of reasonably contain. Though tidy models and Carrot are kind of competing a little bit, but really those are kind of based on well, often they're based on wrappers and those sorts of things. So it's a little bit different. But then using an API, which we just learned about, an application programming interface, these external engines then provide access to their store of models to be able to run this stuff and build good code for machine learning applications, essentially from anywhere in the world, and even at scale sometimes, depending, of course, on the size of the scale. But perhaps the most widely used machine learning engine out there is called TensorFlow. So in their words, they're an entire ecosystem to help you solve challenging real world problems with machine learning. Okay, it sounds great, but what does that mean? Well, pretty much what it says. They've got a store of model architectures developed by TensorFlow staff, and then they make this stuff accessible via a variety of tools and avenues. And perhaps the simplest and most common way to locally access TensorFlow is through a high-level API called Keras. Okay. So Keras was originally developed in Python, and Python probably is still kind of the predominant approach to accessing in the context for use of TensorFlow, I'd argue. But Francois Chollet and J.J. Allaire, who invented RStudio, made a great R port to be able to access all the functions and flexibility from Python's Keras, but locally in R. Okay, they even wrote a couple of books on the project, deep learning with Python, deep learning with R. So at this point then, we've got TensorFlow via Keras run locally in R or Python, okay? But for bigger applications, TensorFlow, to access TensorFlow's power, or the power warehouse, you can use distributed computing or cloud computing context. That API is called distribution strategy, okay? It's got a little more flexibility, but it's typically for more complex uses, okay? So in general, Keras does more than enough for small to medium scale applications. Another really widely used and kind of increasingly growing machine learning engine is called H2O. And so their whole focus is on so-called democratizing AI for everybody. So in short, what they do is based on a lot of open source tools and technology. H2O offers also this massive store of machine learning architectures and code, but for a range of users, from really beginning machine learning developers to some pretty complex stuff. So they also have a range of free and also not so free services that serve this goal of democratizing AI. So for example, the main feature is H2O, it's what it's called. And they use, so H2O uses a programming language like you already know, like, I think Charles Coleman's mic's on. Okay, there we go. Okay, so anyway, H2O is kind of the main feature, and you can either use a language or you can use H2O Flow, which is just a graphical notebook for interactive interaction with H2O, but it's using no code, okay? Or you can use Sparkling Water, which combines H2O and Spark. For example, you can make a query using Spark SQL and then feed the results into H2O, build a model, make predictions, and then use the results again in Spark, and so on. So really, this just allows for like really big data and scalable machine learning applications and so on, okay? But regardless of the approaches to this kind of stuff, these, the common goal of all of these machine learning engines is to just make machine learning and AI research and work just more accessible. And again, this just drastically produces or kind of pushes the boundaries for what we could think or do locally, even just compared to a couple of years ago, okay? All right, so with that as just kind of a quick introduction to a machine learning engine, I want to just quickly go over the basic neural network architecture because I'm unsure of who's in the audience and your background, your level of training. So this is just going to be a quick, probably less than helpful, but hopefully a little helpful overview of neural nets, and so we can understand a little bit of what we're applying here. Okay, so again, to understand the more complex stuff like deep neural networks and autoencoders and all these fancy neural-based learners, it's important to just kind of take a step back and understand very, very generally how our brains are processing information, okay? So in our brains, we've got neurons and they have a cell body and a nucleus and dendrites, and these dendrites take in inputs or stimuli, and then we've got an axon which renders the output to other neurons, okay? So, it's splitting that signal that's received from the dendrites, all right? So the result then is we get some perception of the world based on this processing of raw information, okay? Now, the actual processing is extremely complex, and but the output is typically something that's digestible. In other words, like we know what we can see, we just don't necessarily, we can't necessarily describe how we got there, okay? So at its core, then, this is what a neural network is doing. It's emulating this receipt of raw information, complicating how it's processed, running back through the data, revisiting trends, and fine-tuning expectations using multiple representations of the data, in other words, learning. And then ultimately, it's rendering some conclusion or an output based on how that raw information was processed, okay? So for example, suppose we see a tail, we feel some hair, and then we hear a bark, okay? So our brains are taking these raw inputs and it's outputting some conclusion that we're experiencing a dog. And again, this is the actual biological perspective of exactly how this processing is going on is incredibly complex, and we don't really understand what's going on in the processing of information, at least fully, and the same thing is true in the neural net case. But we do know what the output should look like, okay? And so we can develop models then to process raw information and see whether this output comports with our expectations of the world or some phenomena of interest, okay? So at its simplest then, a neural network, or perhaps the simplest neural network, I should say, is something called a feed-forward, fully connected artificial neural network, all right? And this includes 3 layers. It's got an input layer, which is just the raw input, so the raw features. It's got a hidden layer, which is where information is processed, and then it's got an output layer, okay? And this is just the number of dimensions, all right? And so note this hidden layer usually is considered the black box part of the model that freaks a lot of people out. It's the source of a lot of controversy in the field. But putting that aside, our goal with this kind of a neural network topology is to pass data through the network in small batches and then iteratively tune and train this learner to generalize well. And we can use these for classification problems or regression problems and so on. So by tuning, what I really mean is we've got a bunch of hyperparameters or parameters that kind of apply globally to the model. And this will then impact our solution, what we get out of the network. So there are tons of hyperparameters and tons of considerations dependent on the context. I'm just gonna quickly glaze through a few key hyperparameters. And for the sake of time, I'm not gonna go into a ton of depth, but obviously feel free to reach out to me directly. I'd be happy to talk to you more about any of this stuff, including the code. But the first and most important hyperparameter to consider is the number of hidden layers, okay? So in the basic artificial kind of vanilla neural network case that we just talked about, with a single hidden layer, this is called a shallow neural network. Now, as we add hidden layers, we are deepening the network. It's getting bigger. It's complicating, forward and backward passes of the data through the network. This can be good. We might get more precise expectations or better performance. But it can be bad in terms of it increases complexity. It's less clear of exactly how information is being processed, and it can potentially lead to overfitting the data. So, but nonetheless, when we think about deep learning, what we're talking about is a multi-layered neural network or multi-layered perceptron, okay? And usually, it's not always the case, but all right. So the next main hyperparameter is the number of neurons to include in the hidden layer, okay? And so here, again, the key question is how many, okay? There's no right answer to this, but a general rule of thumb is it should be less than 2 times the number of input nodes or the number of input features. As we include more, it can quickly lead to overfitting. And indeed, in like a case of an autoencoder, when we have more neurons or more nodes in the hidden layer than we do in the input layer, this is called an overcomplete autoencoder, and it can complicate things. There could be reasons to do it, but nonetheless, we'll put that aside for now. So a simple heuristic might be, the number of, it should be somewhere between the number of input nodes and the output nodes. So the input and the output layer. So I'll leave that for now. And then next we've got activation functions. So this is the meat of the hidden layer. So this is where the processing is happening. So I'm not gonna go through all of them again due to lack of time, but very generally, and with some expectation, a nice starting place might be like if you've got a regression problem, you might use a linear or a ReLU, a rectified linear unit activation function. Or for like a basic classification problem, you might use a sigmoid classification, a sigmoid activation function, which is just bounded between 0 and 1, looks like an S curve. Or a generalization of that is called tanh, or the hyperbolic tangent activation function. So on a scale from -1 to 1. Or perhaps you might use softmax activation for multinomial classification tasks. But again, the main kind of point here is that you'll have to think about how data should be processed as you go forward and backward through the network. Also, actually, I feel like I'm running low on time. So I'm actually gonna go more quickly. So we've got the learning rate, how big of steps or small steps to take forward and backward through the network. We've got the number of epochs, and an epoch is just how many times the network has seen the full set of data. You need to consider that. Overfitting is a threat, as always, and then when to stop, or in other words, what defines convergence of the algorithm, okay? And so in a nutshell, in a neural network, we're starting with raw inputs. We initialize some random prediction using random weights, and weights are just numeric values assigned to the connectors, connecting all the nodes across all the layers. The biases are the numeric or transform values that exist in each one of the neurons in each one of the layers, okay? These are the things we're updating, and as we automatically update through backpropagation to work back through the network, this is the learning process, okay? So as this process is automated, we're learning better, some kind of better representation of the data, and hopefully that representation generalizes well to some new unseen set of data, okay? So the process of tuning a neural network is typically more of an art than a science, but it's kind of tricky sometimes. But anyway, so let's take a look at some code, see what this looks like in practice. Here, our task is going to be to predict legislative effectiveness scores. Though flawed in a number of ways, it's a nice continuous measure, so it's a simple regression problem. The higher the value, the more effective a member of Congress is at seeing their legislation through the chamber, let's just say. There's a book and tons of papers on it, but we'll stick with that for now. That's in the Congress data set. And so let's take a look at the code then. So here are a couple of packages, and for this regression problem, we're gonna be using TensorFlow and Keras, and we're gonna be building a basic shallow artificial neural network that we just talked about, okay? So we'll load the packages, we'll read in the data, and the data, we're just gonna grab these couple of features. So here's our outcome, and then these, the year they're elected, the vote percentage they got, their ideology, and then their level of seniority, which is a real valued integer. These are the things we're going to use to predict effectiveness. Now, there's a ton of missing data, as we can see when we skim the data. So these next few steps that I'm not going to cover because of time are just for imputation using the recipes package in R. It's a super handy, really great, simple package to use. It's very powerful. So you can follow those steps if we want to impute missing values, which we do, or we can just take a look at what the pattern of missingness is. This is what that looks like. But here's where we'll start. So again, I've only got a few minutes left even still, so I'll go pretty quickly through this. My apologies. Again, reach out if you've got questions. All right, so let's see here. So first, we're going to set the seed so we can, for replication value, and especially when you use any kind of an iterative sort of a process, you need to set the seed, as I'm sure most everybody knows. We're going to split the data into training and testing sets. Oops. And then we're going to normalize, and then we're going to do the same thing for the test set. And we're going to pull out these values and store them in separate objects. And then here's where we actually build the model, okay? So first thing we have to do is we have to initialize a model space, and then we have to define what the topology looks like in that space. So basically, we're just initializing some kind of a model, and then what we're doing is we're defining each of the layers, but we haven't actually passed data through it, and we haven't back propagated yet. That'll be the next step. But basically, the key here is these are the layers in the network. So here's our input layer. It's just saying, just using this nice base R function, it's saying just the number of dimensions should be how many input features we have, okay? And then we've got our hidden layer here using ReLU activation, rectified linear unit, and then our output, which should just be 1 in this kind of a regression problem world. Here, you don't have to include metrics. This is just for accuracy. This is for information loss. And this is the algorithm that helps us to optimize. And this is just the RMS prop algorithm. There are tons of options out there. So I encourage you to take a look at that. So what you do then is we create this, the shell, and then we can define, I like to define the number of epochs externally, which is 500 in this case, takes about 17 seconds to run. And then we actually fit or train the model. And here we're training and validating, training, validating. So we're training, recall how we set up the data earlier, we're training now on 60% of the data, we're validating on 20%, and then we'll test down here on the remaining 20%, okay? So let's see, it should take a couple more seconds. And, 22, sorry, I was off by a few. And we can then plot what the training process looked like. As we expect, training error always goes down. Training error always goes down because it's learning more features of data across the epochs. But what we can see is that where the validation error, which is what we really care about, starts to level off here about 150 epochs or so, all right? So if we were going back, we might tune at this value, but let's just keep going for now. We generate predictions using the test set, and then we can compare the legislative effectiveness scores for our training and our test sets, okay? And so the blue bars are just those values predicted for the different sets, okay? So this is just the raw value, and then here is the predicted value over here on the left, all right? So I've got 1 minute left. I'm gonna quickly say what autoencoders are, and then I'll be done, okay? So very briefly, an autoencoder is just a neural network approach to an unsupervised problem. We've got 2 stages. It takes the full feature space, but it's unlabeled, and then it forces information loss. This is called encoding, and then it produces something called a bottleneck, okay? This bottleneck is the reduced dimensional space, so the lower dimensional space. From there, we can draw deep features. These are the same things as principal components and principal components analysis. The second stage then is to use a decoder. The decoder is to try to recreate the original high dimensional input space, but only based on the lower dimensional representation. It's an interesting extension of the restricted Boltzmann machine, which doesn't have a decoder stage, all right? So I apologize, I'm out of time, but the rest of the code here is to walk through building an autoencoder, but using H2O instead. So it kind of changes things on a couple of different dimensions. So take a look at the code and please feel free to reach out if you've got questions or anything like that. So thank you very much.
All right, thank you, Philip Wagoner. We have one question in the chat. Do you see it? Is there a way to use k-fold cross-validation instead of one validation set?
Sorry, I'm muted. Yes, there is. You would just have to define that. Well, how I would do it is I would define it externally, and then I would pass each one of those sets through, I'd pass each one of the sets through the model, and I would train based on different ones. But you can also do that internally as you're defining the topology within Keras. So I'd encourage you to take a look at the documentation, or you can send me an email and I'd be happy to write some sample code and we can talk through it.
Excellent. Could you keep an eye on the chat and reply there if there are more questions?
Yeah, definitely. And I'll also post a link to the GitHub repository there too. So thanks.
Okay. Our next speaker is Peter Baumgartner. Are you out there, Peter?
Here I am. I'm here. Peter to Peter.
Please go ahead.
Coming in clear. All right. Hello, everyone. My name is Peter Baumgartner. I am excited to present at GASP again this year. I'm going to be talking to you today about using named entity recognition to identify substances used in self-medication of opioid withdrawal. And with that, let's get started. Next slide, please. All right. So here's essentially the overview of what we're trying to do. So the opioid crisis is still going on, and it still has a major impact on American life. Just some statistics to kind of set the stage. These are a little bit dated, but I think show the severity of the ongoing problem. On average, 5 lives are lost to an opioid overdose every hour of the day. Estimated costs associated with opioid misuse exceed $500 billion annually. And based on estimates from 2016, 12 million Americans misuse opioids, and for approximately 2 million Americans, that misuse was severe enough to be categorized as opioid use disorder by the DSM-5. So discontinuing opioid use is the first step in the treatment of opioid use disorder. However, discontinuation to abstinence, either directly following treatment or just abstinence, results in severely distressing opioid withdrawal symptoms. And these symptoms often motivate patients to restart opioids after discontinuing them, or even prevent them from attempting to stop at all. So that's kind of the larger context outside of the technical aspect of this problem that we're trying to understand. What we're trying to do here is, assuming that people are going to go through these opioid withdrawal symptoms, assuming they're going to self-medicate with certain substances and effects, can we identify what substances people are using and what effects those substances purport to have using self-reported data from the website Reddit? So next slide, please. So if you are unfamiliar with Reddit, it is a social news aggregation and web content, and most importantly, a discussion website. On the left-hand side here, you'll see what's called the kind of main page for 2 of the subreddits that we pulled data from for this project. The top one there is the opiates recovery subreddit, and the bottom one there is just the opiates subreddit. And the data that we're looking at is the full set of comments and posts from 2015 to 2019. So just to break that down a little bit more, users submit posts to subreddits, which is what you see on the left there, and then users are also able to further comment on those posts to kind of serve as a discussion platform. So we're looking at both the content of the posts and the mostly the content of the comments. In terms of relative data size, the opiate subreddit, as you can kind of see there in their about community, is much larger than the opiates recovery subreddit, and they've also been around a lot longer. So in this kind of full data set I've outlined, about 98% of the data actually comes from the opiates subreddit, and a very small amount comes from the opiates recovery subreddit. Next slide, please. So what we're going to try to do is apply named entity recognition. And on this slide, you actually see kind of the first formalization of this problem as it was laid out as a task from the Message Understanding Conference 6 back in 1996. Essentially, the idea with named entity recognition is that people kind of noticed it was important to recognize information like names, including like persons, organizations, locations, and be able to extract them from text. Kind of more importantly is named entity recognition is really powerful if you need to kind of generalize this extraction process based on lots of examples of those objects and phrases in context. So for example, here you see that they're pulling out person. The idea with named entity recognition is, you train a system to identify what patterns of text indicate a certain span of text is a person. And then it's able to generalize based on those patterns to extract other persons from text that it hasn't seen in the training data set yet, right? So it's an unseen example, but it's able to generalize based off of the surrounding context to pull that information out. Next slide, please. So rather than persons or organizations or any of the traditional named entities, what we are interested in is identifying our own entities and defining them and being able to extract them from text. So on the left-hand side there, you'll see the definitions that we used for our two entities of interest. And on the right-hand side, you'll see examples of these extracted from a piece of sample text from Reddit. So one thing you may notice is that our definitions here are pretty broad and they're not very clinical. And the reason for that there is we're looking at social media data, and a lot of times people use slang and various ways of describing things. There are lots of spelling errors and just kind of interesting non-clinical, non-specific ways of talking about the ideas that we care about. So because of that, we've taken kind of a broad definition of what our entities are and what we're looking for in this text. So on the right-hand side, you can kind of see an example of what this looks like. You see that people are mentioning subs, mdone, kind of as a slang for methadone, H for heroin, diazepam, and then you'll see effects like RLS, restless leg syndrome. You'll see they spell out loperamide, but it's actually misspelled. And so that's kind of the general problem that we are trying to solve with named entity recognition here, and an example of what this looks like. Next slide, please. So how did we actually acquire the data for this data set? So Google BigQuery actually has a public data set of Reddit comments. And so you can actually just use Google BigQuery to filter down to a relevant subset of comments and posts from certain subreddits, and that's exactly what we did here. So we queried basically the entire data set of Reddit, said, show me all the comments and posts from these two subreddits, and we put those in a table, and we're able to export that to a CSV. So because of the size of this data, you can kind of view the data for free, but the overall cost of getting our extracted data set was like $25. So still moderately cheap in terms of data acquisition costs, but not free in order to do all that processing. Next slide. So another way that we acquired the data, when we originally acquired this, we didn't have all of the data. We only had data until April 2019. And the updates to that Google BigQuery database weren't totally in place. And so one of the other things we did is wrote a package that makes extracting and using these monthly data dumps from the push shift service, which is where that Google BigQuery dataset actually comes from, easier to extract and use. And so I want to bring this out as a little bit of shameless self-promotion, but also this is a Julia package, and I saw that Julia was a wanted topic of this conference in general. So if you're curious about an application of Julia, this is actually a great example of that, and I'm happy to answer any questions or talk more about that as well outside the context of this talk. Next slide. So this shows the trend of the number of comments on just the opiates subreddit starting in 2016 to 2019. And the first thing I want to highlight is just the volume of data here. So what you're looking at is just the count of comments. Over this whole time span, we're looking at 2.5 million comments. And I want to call that out because this is, one of the first projects where I've actually had to deal with and think about the size of the data and make plans and write programs that deal with parallel computation and just managing. You have to approach things differently when we're dealing with data this big. It's a lot of stuff that won't just run on my laptop. So that's an important factor here. Another important factor when you have a lot of data is just sometimes very basic stuff here, like the counts, can illustrate some interesting patterns. And so we're currently exploring what is causing that dip starting in 2019 in just the volume of discussion that's happening on the subreddit. It takes a big dip there. Almost 50% of the volume is gone. So there's a lot of data here. The trends are interesting, and there's a ton of kind of interesting research opportunities that just come from the volume of data. Next slide, please. Okay, so a little dense here. Let me walk through all of these steps. What I'm going to talk about is how do you actually start building a named entity recognition system, especially when you're dealing with data of this volume. So my first kind of principle is to solve a smaller and simpler problem. And that kind of gets broken up into two steps. So the first thing that we did was, you have 2.5 million comments. Not all of them are going to have the entities that we care about. And so the first thing we want to do is identify a relevant subset of those documents using a terminology list we derive from word vectors. So what we're able to do here is generate a list of seed terms and say like opiates and some of those effects like yawning or upset stomach, and use word vectors to say, okay, what are words that operate similarly to these keywords, these seed words in this text? And then show me all the documents that match this set of keyword expanded keywords. And that way we're a little bit more sure that we're getting content that's relevant to our specific problem with named entity recognition. The second idea in solving a simpler problem is to build a labeled data set as fast as possible with binary decision making. And the idea here is typically in named entity recognition, what you're having to do is highlight those individual spans of text. And it's just a very arduous task to do that for a full set of entities. One approach that a few data labeling platforms have taken in order to speed up that process is to do binary decision making. And how that works is it will make suggestions about what an entity is, highlight that span for you, and then you just approve or reject that as an entity. And if it's able to do a pretty good job there, you're able to build a lot of labeled examples rather quickly. The second idea is to iterate with the data. So here, your code isn't the only thing you want to iterate on. You want to iterate on your training data set. And what this means practically is think of your initial models as just disposable models. You can still train these pretty cheap. There's not a lot of data. And so what we'd like to do is to get a model out there as soon as possible. And what we do with these disposable models is apply them to the remaining data. So let's say we've only labeled 500 comments. Let's apply it to the remaining 2.5 million minus 500 comments, and then aggregate the entities that it extracts from there, do error analysis on those results. So here we're looking through and identifying things that aren't actually the entities we care about, and then identify documents with those erroneous entities to increase the training data set. So we're going kind of back to the first step and saying, okay, now instead of showing me documents that I know are relevant based off the keyword list, show me documents with wrong answers so I can go in there and correct them and provide higher quality training data to the system to more accurately label entities. Next slide, please. So what does this actually look like? Here we're just looking at the most common substances and effects we've extracted from these two subreddits. One thing to call out is just the abbreviations on the left. So subs Both refers to Subutex and Suboxone. They're both treatments for opioid use disorder and helping with withdrawal. And you can see the effects there. Still need to do some kind of entity linking and cleaning up there, but these are the types of things that it's extracting from the text and the most common ones as well. Next slide, please. So this is performance. I think one big takeaway here is that it is easier to predict substances than effects. And I think we would kind of expect that because effects are a little bit subjective. People describe them in different ways. It's kind of hard to capture a lot of the feeling-based language of some of the effects that we're looking at, whereas substances are a little bit more objective. You know, you can point at them and say, yes, that's a substance. It's a little bit easier to identify those in text. But overall, we do pretty well with F1 score of 88.42. Next slide. A natural next question might be, is 88.42 good? So we're looking at, on this chart, just how much named entity recognition has improved since 2016 on a different task, on a different data set. But what's highlighted here is just we're in the ballpark, right? So in 2016, they were doing about 86 as an F1 score. The latest state-of-the-art models are about 92. And so we're at least in the ballpark with 88 in terms of performance here. Next slide. So we do have some next steps here. What we're going to do is we're continually updating the model with more corrections. So like our top 100 entities are really high quality. They're all kind of what we would expect. And then beyond that, we start to find some things that don't actually match up with what we would expect for these entities. So we're still doing that error correcting process. One of the things we're doing is linking these entities. So behind the scenes, you know, what are all the different ways that people talk about, you know, nausea and vomiting? You saw a bunch of different maybe slang terms for that. Can we link those behind the scenes to kind of clean up the data? We're going to update this model to a new transformers-based model architecture. So moving it more towards the right-hand side of the chart that we saw there with the latest state-of-the-art methodologies in terms of named entity recognition. And then one of the things we can do with this data set is to do a network analysis of co-occurring entities. So we're looking at, you know, which effects and substances are mentioned in the same sentence, and kind of what does that entail in terms of both what substances are people using together, but also what effects are people reporting from certain substances, kind of getting back to our original research question, trying to understand this phenomenon. And I think the next slide is my last one. There we go. So happy to answer any questions. I did put my contact info in the chat as well. If you want to email, I'm happy to answer questions via the chat or asking them as well. Thank you.
Thank you. You do have time for a question. I'm going to read a question from Nathan Cruz. Sometimes subreddits change moderators, add rules or restrictions, or the platform updates its terms of service. Do you have strategies to determine whether the dip you saw in the data was related to the prevalence of content in the comments versus exogenous changes to the Reddit subreddit platform?
Yep, that is a great question. That is exactly what we're looking at now for that dip. One of our hypotheses is in April or May of 2019, Reddit really started to crack down on soliciting illegal drugs. So they tried to shift more towards having a kind of like legitimate marketplace, like a Craigslist for people who wanted to use Reddit to buy and sell stuff. Obviously, prior to that formalization, people were kind of doing it in an informal way where you could message other users and, you know, they didn't have a good way of tracking that. But oftentimes you could see in the older data from these subreddits, they use a lot of kind of like coded secret language. They're interested in buying or selling drugs, or were pointing people where to do that. And so they really started to crack down on that in 2019. One thing to note there is that I think that might be responsible for part of it, but I have a hard time believing that like 50% of the content was about soliciting drugs, just because I've looked at a lot of that content. Like, it doesn't seem to be right, but that could definitely be responsible for some of that drop that we see, is just kind of cracking down on that sort of thing.
Very good. Thanks very much. Please watch
Thank
the
you.
chat box. And our next speaker is Chris Marikoff.
Hi, Peter. I'm here. So I'll try to share my screen very quickly here with you guys. So when I try to put my video on, it says that the host has stopped it.
Devi or Matt, can you fix that?
I'll take care of that.
Perfect. Thanks, Matt.
And please introduce yourself.
Absolutely. Yeah, I hope everyone can see me and hear me.
We see
So my name is Chris. I'm with OMB. There's something called in there, the Office of Information and Regulatory Affairs. And in there, there's a statistical and science policy branch. I belong to that group. We are a bunch of statisticians and scientists that help data and also advise on the regulatory have to be done. Pretty exciting work, a lot of macro level stuff. I'm happy to be here and thanks for having me. We'll dig in shortly. Let me just try to share my screen. Great. Can you see the present?
Yeah, that works.
Great. Very good. Yeah, so the topic of this presentation is to broadly introduce some concepts that have become of prominence in the recent years. And the subtopic, of course, would be to help federal agencies mainly kind of think about how they can leverage natural language processing and organize the vast amount of administrative data they have just laying around. So I just want to point you to where we stand, where NLP fits in that broader ecosystem of AI and fancy terminology, as I know many people use them in different ways. So this is pretty much the schema. We have computer science, artificial intelligence, machine learning under that. And when statistics hits machine learning, we have the statistical natural language processing. And statistics, of course, is important here because there's a lot of prediction that's going on, a lot of classification that we have to rely on for the computer to make sense of the natural language we feed it. So, sorry about the craziness. So why statistical NLP now? We have seen a lot of advancement with respect to machine learning. Most recently, though, two things in particular hit us. Great presentation by Philip beforehand to introduce the neural networks. And now we have to deal with graph neural networks, introducing even more complexity, but making a very, very important breakthrough. I will just, if I have time, I'll briefly talk about that, but I also want to mention the BERT algorithm approach. BERT stands for bidirectional encoding of respondents from transformers. You don't have to memorize any of this. Just think about BERT as a breakthrough. It comes from a paper recently published by Google. They tested it out on a large amount of text, including Wikipedia and all of the Google books, corpora. So it's pretty good. Of course, it really matters how much data you have when you're training and subsequently classifying. Just a second here, sorry about that. Of course, we have the amount of data, we have the distributed computing that's helping tremendously with respect to the graph structure, inherent graph structure, and of course, neural networks won't be possible as a whole without distributed computing. So very early on when NLP kicked off, so this was the main problem we were running into, right? We use words, but they have more than one meaning. And really to sort that out, the ambiguity we were creating, we had to come up with something really precise as far as prediction. And so we talked early on, NLP wasn't really a very big thing because statistically and computationally we weren't there. And so folks came along and really reinvented the approach where natural language processing is now, you'd have to have that probabilistic component to it for a precise classification, right? And if you think of language as probabilistic phenomena, in other words, what is the next word that comes out of my mouth has to do with a ton of things that happened in the past, right? And we are allowing the classifiers to predict that based on a previous content that I have created. So it's relatively simple, but we have to have that presumption in place for this to work. So again, the meaning of a specific words have more than one meaning, of course, and we used to classify them based on previous uses coming from grounded in subjectivity, right? Coming from the same author, same corpora. That's how it learns, and that's how it classifies. Solving this ambiguation is the primary problem. And of course, we see here that if you think of text and you think of sentence, so you think of words, first of all, then you think of sentences, and then you think of sentences organized in paragraphs, and then paragraphs within documents, and documents within corpora, and you see how much of a structure we're talking about, right? There's a lot of things to take care of in relational terms, right? It becomes a place where relationships, sequence, and structure really matters. And that's where graph data models really come into play and help us out orient ourselves. All right, so very basic NLP stuff here. So we spoke about subjectivity in creating content. And if I tend to use a bunch of expressions every time I speak up, then the computer catches that up as patterns, right, in my content, and it makes it easier to classify things. Tokenization, that's the micro level dissecting of the text, essentially word by word within a sentence, for the computer to make sense of things. We would have to define where a word starts and where a word ends, right? For the computer to read it and analyze it. So we also have the word normalization here implies that words can have more than one meaning. And many times the computer needs to perform stemming, right? To chop things up and just work with the stem of a word to understand what's that particular sense. And lastly, we have the sentence segmentation and parsing, which are critical as far as sentence prediction, right? What meaning comes after what? What's the actual order in a corpora or in a document or in a paragraph that the computer can pick up and help parse the content. Great. So some of the applications very quickly of NLP, natural language processing. You can see all these thus far. I think we'll jump to graphs, graph data models now, and I'll do a very quick demo after that before we introduce the concept of knowledge graphs. So what is when we say graph, graph is just a mathematical representation of relationships between data. That's how you can think of them. And it really matters for us from a data standpoint when relationships are pretty important, right? You can think of a graph, and I have an image of a graph. I probably should should have started with that. So if you think of the red rectangle or square here in the very middle, this is called a node. This is an entity or a vertex. Some people call it a vertex. And you have those yellow links or edges, which quantify the relationships of that node to its adjacent nodes. So this becomes very important from a mathematical standpoint, because you can see how data could be data and information for not only for the particular node, not only for the relationships, but you can spin a whole amount of mathematical calculations for the adjacent nodes as well. And so this becomes really critical in NLP and pretty much in graph data models as a whole. So you have data encapsulated at many different dimensions and many different levels with graphs, and it's very easy to retrieve and work with. So coming back to this slide, introducing graphs with NLP. So if there's one thing you take from this presentation, and I mean that literally, just think about text and NLP and graphs in the following way. So you have words, sentences, paragraphs, text and corpora, documents and corpora. And so within that, to parse that, the computer needs to understand the inherent structure. So within parsing, we have graphs at 3 levels. The first level would be parsing. The second level, to solve the problem of disambiguation and be precise as far as classification goes, the computer needs to employ, in many instances, neural networks, and they are very, very powerful, which also have inherent structure. But even deeper than that, the graph neural networks, which have a graph structure that allows states of nodes to be passed to inform on the neighboring nodes and making that neural networks even more convoluted. So graphs play a critical role in 3 aspects. We had parsing, we have disambiguation classifications through graph neural networks, and the final area, which I think is critical to knowledge graphs and to the end user. We're all end users. So retrieval and storage here is only enabled in a performance savvy way to, again, replicating the nodes and edges structure to grab the text and analyze it, right? So this is how you can have the Google Books, for example, this entire corpora rendered into a database. In a relational database, this would essentially be impossible, right? You won't be able to retrieve, and analyze such amount of content. So three critical ways. So here I'll just demonstrate a use case that came to my desk here at OMB that had to do with natural language processing and to an extent graphs. So there was a regulatory language published, I believe 6 months ago or so, that had to do with AI, essentially establishing ground rules for privacy, data privacy, confidentiality, non-biased use of AI throughout the country and within the government, of course. So in that domain, OMB received deals with a bunch of public comments, right? We had to address them, and because AI is such a hot topic, we got a fair amount of comments, in the hundreds, nothing crazy. Sometimes we get in the thousands and the tens of thousands, in the hundreds, but the content of the comments was large, right? We were talking in the amount of comments in the hundreds, but then we got hit by everyone in that AI landscape, and they wrote papers and we received them, what they think of AI. So it was a jungle pretty much. And we had to make sense of that pretty quickly and see who is behind what. I'm sorry about the craziness again. So first of all, I threw that all of that content from the regulations.gov, and we have an internal system called Raucous, into a software tool called Inspire. It's an NLP software tool, a quick plugin here for the developers. This is something that came out of the Pacific Northwest National Laboratory software. And for those of you coming from a federal government, this is free for you to use. It's free for US government use. It sits out there. You would have to only request it from PNNL, and they will send you that. So it's a pretty powerful tool to quickly analyze text, and I highly recommend it. I apologize again. Okay. So you can see all of the language landscape here that the corpora that we're dealing with, and you can see that the topping mapping that the software was able to perform on that corpora. At first, you can dissect it yourself. To the right-hand side, you have the focus ignore boxes that you can plug in terminology or stuff that you're interested in. But then the groupings underneath are pretty important. You have, we saw the previous presentation from Peter on entity, named entity recognition. So entity extraction is, of course, key to NLP making sense of data. So you see a ton of groups here, groups of entities, and you can help software classify those even further. But even starting here with organizations gives you a very good idea of who submitted comments, what the themes were, and how to address them. So on the once I got like basic understanding of what the landscape looks like as far as topics, I then evoked the classic theme view that software on the corpora. And so what I was struck by is if you see something like that, so this 3D map shows you the amount of content and the themes, the overarching themes. But so the moment you have just 2 or 3 topics or a limited amount of topics, you know that something's going on with the data, right? This is not only relevant to NLP, but pretty much all of the data. You have some skewness going on. And so I was really struck by the HUD. You can see the HUD thing in the far right corner. And I wanted to understand what that is, why HUD is associated with the Department of Housing and Urban Development would be associated with AI. So very quickly, you can, I'm sorry, Prezi is wild. Very quickly, you can, so I just double clicked on the HUD, team, and it brought me all the content that pertained to HUD and why actually HUD is a topic of interest with a large amount of content here. So it turns out that there's in the housing lending, like mortgage landscape domain, HUD is proposing to use some form of AI. And so many people were very vocal about that. There are some genuine and founded concerns about bias in there. That's what I understood very quickly. But more importantly, for my purpose of analyzing those comments, I had to be able to very quickly understand what HUD was about and then group and put those aside to allow and dig into the rest of the content, right? So this is what I did. And once HUD was removed, you can see that that initial 3D topping map was looking very, very differently. And now I started deriving sense of what the different comments were about. So this is my very quick demo here as part of that presentation of the Inspire tool. But I hope this allows you to think of language as a something that's here for the taking, right? In your agency, your organization, you can leverage layers of textual information, bring all that together and explore it and analyze it. Great. I am coming to the 1 minute warning, and this is fine because I just have to introduce the concept of knowledge graphs and I'll be done. So knowledge graphs are essentially they allow you to go across organizational structures and divisions, departments, what have you, and grab things. Grab, for example, emails, grab policy documents, grab like historic program research that you had to deal with, and bring it all together. And once you do that, you see a lot of common themes or overlapping themes. And sometimes this is good, sometimes you might uncover a lot of problems with a specific program or within a specific organization. You have access to the slides. You can read my notes here, but most importantly, that structure underlying a knowledge graph. So knowledge graph is powered by two things. You have the NLP, the ability to leverage text and analyze.
Forgive me.
And then you have the graph data model underlying. Very good. All right, so I'm coming to, at a time, and I thank you for attending. And if you have any questions, just hit me in the chat. I'll be here. Thanks.
Thank you. It's very interesting. Please watch the chat. Our next speaker is Gizem Korkmaz.
Hi, can you hear me? Okay.
Yes.
Thank you very much. First, I'd like to thank the organizers for such an interesting event. All the talks were very interesting to us. My name is Gizem. I'm part of the research faculty at UVA Biocomplexity Institute. Today, on behalf of our team, I'll talk about our research project on detection of innovations using text-based data sources. But before I start, I would like to acknowledge my co-authors. This work is an academic and federal government agency collaboration. We work with colleagues from the National Center for Science and Engineering Statistics at the NSF. Among the members from our research group at UVA, I would like to highlight our junior research scientists, Devika and Neil, who have contributed to every aspect of this project. And they're in the audience now, so during my talk, please feel free to use the chat to ask questions, and they will be happy to answer them. Next slide, please. So the overarching goal of this project is to see whether it is feasible to use non-survey data sources to measure business innovation. This is traditionally done by surveys. As I mentioned earlier, this project is in collaboration with colleagues from NCSCS, and they provide statistics and data through surveys on R&D and innovation activity. In particular, they conduct the Business R&D and Innovation Surveys, BRDIS, to collect information from US companies. The screenshot that you see in the bottom shows the question asked by BRDIS to capture innovation that was done by the companies. So they ask whether they have introduced something new or significantly improved goods or services in the market. So the goal of our project is to see whether we could use alternative non-survey data sources to complement and enhance surveys like the BRDIS. We're developing natural language processing and machine learning methods, and we focus on text-based data sources to do so. We will focus on product announcements, press releases, and financial filings of companies to be able to capture the innovations that are introduced by these companies. Next slide, please. So, and now let me talk about our current focus. So we are currently looking at product innovation. As through the project, we have learned that we're more likely to find this type of innovation in publicly available data sources. We're using the Oslo manual definition to define product innovation. Based on the Oslo manual, the product needs to be new or significantly improved, and it needs to be available on the market. Second, we're focusing on the pharmaceutical industry to start with. The reason is that there's a high rate of innovation in this industry. So we can actually capture some of this innovation using these different methods. And it is a regulated sector such that before products are available on the market, they need to be approved by the FDA, as you may know. And these approvals are publicly available. So this actually provides us a good ground truth data to validate our findings. Our initial focus is on financial filings and news articles as our text-based data sources. And we're developing innovation indicators, which we currently define as counts of new products by companies by each year. Finally, we would like to validate our indicators using the listings provided by the FDA. Our goal is to develop accurate, repeatable, and scalable methods so that we can study multiple sectors using these methods. Next slide, please. So in this chart, we're summarizing the data and the methods we're using and planning to use. So this study involves two parallel and complementary tracks. On the left, I'm showing you the natural language processing, NLP track, which refers to the text mining algorithms we're developing to capture the innovation in the financial filings of the companies. So I'm talking about the SEC filings that the publicly traded companies file every year. On the right, we look at the machine learning track, which refers to models that we develop to identify news articles that are likely to mention innovation in them. So let me go a bit deeper into each track here. First, in NLP track, we have developed 3 different algorithms to identify potential innovations in these filings for each company. And we're defining these potential innovation using additional dictionaries that we have developed so far. Then we compute standard metrics such as accuracy, precision, and recall to evaluate these indicators using the publicly available data source provided by FDA, as I mentioned before. In the machine learning track on the right, we use a labeled data set to start with, labeled news articles that mention whether there's an innovation or not in these articles. And we're training different machine learning models to see whether these articles are likely to mention an innovation or not. And then we test the performance of each model, again, using standard metrics from machine learning. Next slide, please. Now I'll briefly mention the data sources that we're using. As I mentioned, our reference data set here is the National Drug Code Directory, NDC data set that is published by the FDA. It includes over 100,000 listings from 7.4 thousand companies in our data set. We use this data set as our ground truth that represents the set of all drug listings across the company. It provides drug information, including the labeler, the marketing date, product name, and the product type. So the bar plot on the right shows the total number of listings per year for our study period. You can see the increase there. Next slide, please. As I mentioned before, we use the annual financial reports, 10K filings of publicly traded companies for the NLP track of our study. So this is our first text-based data source that we use for this purpose. We collected and scraped over 5,000 filings from almost 800 companies that are in the pharmaceutical sector. This data was scraped from SEC's Edgar database, if you know about it. Next slide, please. Our second text-based data source is the news articles about pharmaceutical industry that were collected and distributed by Dow Jones. We observe that these articles describe various topics in them. So we identify articles about clinical trials, FDA approvals, product launches, and even mergers and acquisitions are mentioned in these news articles. We have obtained around 1.9 million articles corresponding to over 1,400 different publishers here. And you can see in the bar plot on the right, the top companies that are mentioned in the news articles. The thing is that the DNA database also includes regulatory agencies, which are shown in orange there, as mentioned as a company in the dataset. So we have to also clean them up when we're looking at the companies that produce these innovations. Next slide, please. So here, we're actually giving the details of the NLP methods. I'm talking about the royal we, had a lot of challenges with the text ingestion, cleaning, processing, which I don't want to get into today. But our resource scientist, Viveka, is currently developing a package and documenting all that process she had to go through. I would like to highlight, though, the 3 algorithms that we use here to capture the potential innovations that I talked about. So our first method extracts all non-English words as potential innovations from the filings. So as you know, in the pharmaceutical sector, products are usually given names that are not used in daily English language. So we said that, okay, let's take all the filings and extract the non-English words and take them as our baseline model. These are the potential innovations for each of these companies. So that's our baseline algorithm. In the second algorithm, we chose those non-English words that are close to 20, that are within 20 words distance of particular keywords or phrases that we have chosen. So we have chosen words such as launch, new product, and new drug, and we look at non-English words that appear close to these keywords that we have chosen. And this is our second method. Finally, in our last method, which is the most strict method, we look at the registered or trademark symbols next to the words, and we take them as our potential innovations. As you can understand why this is strict, because not all the companies will use those symbols when they are filing the 10Ks. So then we obtain, using these 3 methods, we obtain a list of potential innovations by company, which we then compare to the listings, their listings in NDC. Next slide, please. So here I'm showing you the results for method 2, which is the proximity. So the words appear close to product, a new product launch, and words that which we've chosen in our method. So on top, we have 2 histograms you can see. These show the potential innovation counts before and after the refinement that we have applied. The refinement includes developing dictionaries that are not innovations, but that were introducing some noise to our data. So we actually, we got rid of other company names, some regulatory agents names, and some terms that are used in the pharmaceutical industry. So that allowed us to refine some of the potential innovations that we have identified. So after the refinement, we see that most companies have below 50 potential innovations. So looking at the bar plot in the bottom, we can also see the top 10 companies with, that introduced all these potential innovations, right? So on average, we found that this method identifies 40 potential innovations per company. As I said in the beginning, and which is the main point here, our goal is to enhance the surveys that ask a binary question of whether they have introduced something new or not. So this is the question that is asked to companies, and they answer it as yes or no, right? So here, what we see that obtaining the counts of innovations by company is already a complementary measure to these surveys, because you do not really know from the surveys how many innovations they have introduced, but you know that they have introduced an innovation. Next slide, please. So here we're showing the evaluation metrics we use, but I don't think we need to talk about them in this audience because everyone is familiar with them, except that I just want to highlight here, our validation problem is once we determine these potential innovations, whether they exist in the NDC. So this is how we are validating our methods. Next slide, please. So here we're showing the average precision and recall we obtained for the 3 methods that we have used. So method 3, as I mentioned, which is our most strict algorithm, which looks at the trademark and registered symbols next to words, results in the highest precision, which is expected. So it shows that on average, 39% of the potential innovations we have identified using this method, they were true innovations listed in the NDC provided by FDA. However, since this method is very strict, the recall values are not as high as precision, as you can see on the table. When we look at method 2, we see that we have an average recall of 80%. And this implies that on average, 80% of the true innovations in NDC, I mean, 80% of the listings in NDC were actually predicted using the filings and the methods that we have developed. Next slide, please. So here we're also showing as examples some of the drugs, some of the innovations we have identified from the listings of TIVA. And we can see that, you know, our method actually is able to capture multiple innovations per year, so which is a complementary measure to the burdens that I was mentioning before. Next slide, please. So now I'm going to talk about the ML track of our study. So here we have a set of news articles, and our goal is to use the features of these articles. Okay, 5 minutes is good. When I say features, I mean the word frequencies, words that are used in these articles, and we want to estimate each article's likelihood of mentioning an innovation. So that's our first goal here. So how can we identify articles that are about product innovation, that mention an innovation? To do so, we of course need a labeled data set. So we actually use over 500 Dow Jones news articles, and we have manually labeled these headlines and asked the question whether they mention an innovation or not. And we're using this as our training data. After that, we use a series of text pre-processing steps to clean and prepare the articles for the machine learning models. Here again, it's the royal we. Our team member, Neil, effectively overcame all the challenges with respect to the cleaning of the text and pre-processing. And I have also listed here the 4 different machine learning algorithms we have used to start with, and we're using open source tools such as NLTK, scikit-learn, and XGBoost to implement these machine learning algorithms. Next slide, please. Here, as I said, our classification problem is to determine whether an article is about innovation or not, which is a hard problem. And we're using all these headlines to do so. These models were trained using a subset of the news articles that we have manually labeled. Here in the table, you can see the training and test sets that we have used for each method. That's where we summarize how many articles were labeled as yes innovation and how many of them we're actually using for training our methods. So, after training these models, of course, we're using out-of-sample testing to evaluate the machine learning methods using the standard classification metrics such as the accuracy, precision, and recall, as you can see. And we also look at the area under the curve. Here, one additional thing we have done is that we developed a baseline method, which was a smart baseline. We actually consider each article, our prediction being it does not involve an innovation. So I'm gonna explain that again. So we developed a baseline that predicts that every article's probability of mentioning an innovation is 0. And the reason we chose this baseline is that only 9.3% of the articles were actually about innovation. So this is quite a smart baseline. And we also see that it performs relatively well. If you look at the table, it has 92% accuracy that we observe. In addition to that, we also have decision trees and XGBoost that result in very high performance. Next slide, please. So we can skip this one. Here we give some examples of these articles that models predicted as yes or no, and we see some overlaps between these methods. So some methods are actually predicting that these articles include innovation, and some of them are cannot capture that. The last 2 articles we see here, none of the models can capture them. Next slide, please. And this is my final slide. So what we have seen here is that using natural language processing, we have identified around 5,000 potential innovations, 40 innovations on average for each company, which is a metric that is missing in surveys. This framework is independent of the sector, so we can actually apply this to different sectors of the economy. Second, we're developing machine learning methods using news articles, and we have evaluated using standard performance metrics. And we have obtained very promising results, such as accuracy about 95%. Our next step is actually, referring back to the previous talk, we want to use named entity recognition, such as BERT, to identify organization names and product names in these news articles. With that, I'll pass it on to the next speaker. Thank you.
Thank you. That is great. There is time for a question. I don't see one in the chat box. I guess I'm curious if the product innovations are very often linked, in your opinion, to scientific innovations, or if it's really a different thing.
What do you mean scientific innovations?
Chemistry.
I know. So here we're only considering the products that are introduced by companies, and the definition we're using is coming from the Oslo manual. So these are products that are introduced by companies that are new or significantly improved and that are available on the market. So that's the definition that's what we're using.
I understand. Awesome. Okay. Please watch the chat box. There might be more questions. And our next speaker is Andrea Erculescu, right?
Yes, thank you.
Go ahead.
Thanks, Peter, and thanks, Davey, for flipping through the slides. I'm Andrea Erculescu with Westat, and I will talk to you about adopting prior distributions for the variance-covariance matrices to fully specify an area level bivariate hierarchical base threefold model for proportions of adult competencies. And hopefully in the next few slides, I can unpack this title. Next slide, please. So first, I'd like to acknowledge the team members. This work is part of a large project that we conducted for NCES, and the methodology report is available at this website. So with that, Tom Krenske, Laila Mohajer, Jane Lee, Bob Fay, Weijia Ren, Wendy van der Korf, Lynn Lee from Westat, and John Rao from Carleton University. Next slide, please. So the motivation for this work is estimation of adult competency in the US at granular levels, such as county, state, census divisions. And as part of the final project deliverables, the team put together a US skills map, which is available online on the NCES website, where you can find county level indicators for literacy and numeracy for all the counties in the US. And this is an example, it's a snapshot of literacy rates, and specifically percentages at or below level 1. And notice at the bottom, I'm mentioning the proficiency levels are defined in terms of the scores that the adults scored on the assessment. So level 1, it's defined with based on the scores that are 225 or below. And I'm hovering over Story County in Iowa, so you can see that 11% of the adults are estimated to have literacy scores at or below level 1, compared to 15% for the state of Iowa or 22% for the nation. So how did we actually do that? Thank you. So in this talk, I will focus on estimation of the proficiency rates at or below level 1 and at or above level 3. And for that, we developed an area level bivariate hierarchical based threefold model. And to unpack this, area level, because we are modeling county level survey estimates and associated variances, as well as auxiliary data available at this level. And by survey estimates, I mean, we first combine sample data from the US program for the International Assessment of Adult Competencies, or PIAC, for 3 cycles, 2012, 2014, and 2017. And we had sample available for 184 counties that we can actually work with to develop the model. For the rest of more than 90% of the counties in the nation, we constructed predictions based on the model. It's a bivariate model because we jointly modeled proportions at or below level 1 and proportions at or above level 3, so that we can borrow strength from the relationship of these 2 proportions. We specified the model as a hierarchical base model so that we can account for different sources of error. So we have a sampling level for the survey data. We have a linking level where we link the survey data with data from auxiliary sources. And we have prior distributions for the model parameters. So in this way, we borrow strength across all the counties, and we also borrow strength from auxiliary data. Moreover, we specify the model using a threefold specification so that we can borrow strength from the nested structure of the geographies. We know that counties are nested within states, within census divisions, and estimation and prediction is necessary at all these three levels. Next slide, please. So mathematically, we can write down the model in this way. So you notice that the first level, it's the sampling level for proportions. So Pijk would be a bivariate vector for the two sets of estimates, proportions at or below level 1 and at or above level 3. And we assume that they follow a normal distribution with mean theta ij and known sampling covariance matrix sigma ijk. What's of interest is theta ijk. So those estimated proportions at the two levels. And in the second level, the linking level, we link the survey data to auxiliary data that we denote here by xijk that was carefully selected for this model. And the threefold specification comes in using the C, V, and D latent effects at the county, census division, and state and census division levels respectively. And finally, we adopted, previous slide, please. And finally, we adopted prior distributions for the model parameters. For the regression coefficients, a normal distribution centered at 0 with large variance. And in this talk, I will focus on how to specify prior distributions for the variance covariance matrices at the three different latent levels. Next slide, please. So in the literature, I refer to the Gelman 2006 as a very useful paper on discussion of prior distributions for standard deviation or variance parameters in hierarchical Bayes models. And those are for univariate, specifically univariate models. And some common choices are inverse gamma distribution for the variance parameter, or a uniform distribution for a variance parameter, or half Cauchy distribution for the standard deviation parameter, with the last one being performing better specifically for hierarchical Bayes model, where the latent parameters are nested, or there's a small number of latent parameters at the different levels. I'm not aware of such a discussion for multivariate models other than Alvarez, Naemi, and Simpson, where they basically compared two different prior specifications, the inverse Wishart and an LKJ type, for their specific applications. And I do want to draw some connections with the univariate level models. The inverse Wishart distribution marginally boils down to inverse gamma distributions for the variance parameters, and the LKJ marginally, it's a uniform distribution for the correlation parameter. And LKJ prior, it's based on the decomposition of the covariance matrices. Next slide, please. So for specifying the adult competency proportions model, we also started with a common prior distribution, the inverse Wishart, which has very nice properties, especially computationally. It's conjugate prior, so things work out very nicely. LKJ type prior, however, it's also available in the RSTAN software, the software that we use for this application. And for the LKJ type prior, we looked into two types of specification. One, where we applied the LKJ prior for the correlation matrix and half Cauchy priors for the standard deviation parameters. And the second type, where we decompose the correlation matrix using Cholesky decomposition, and we apply the LKJ prior on the Cholesky factors. Next slide, please. And throughout the talk, so the LKJ type 1 prior would be denoted as the original prior, because this is the prior that we adopted for the final model based on the performance and all the model evaluation that we conducted. And I will compare the performance of models specified using this prior for the three levels of covariance matrices with the performance of models specified using an LKJ type 2 prior. So I denote that as an alternative prior. And also the performance of models using the inverse Wishart distribution. Again, that's denoted as an alternative. And the different models are fitted using RSTAN, MCMC, using 3 chains. We started with a large number of iterations. We brought in the first few thousands, and then we did some teething. So we kept 4,500 iterations for inference. Next slide, please. So this is GASP workshop, so I like to have some code in my slides. this slide and the next two will show you how to specify this type of models in RStan. So this is the specification with LKJ type 1 prior for the 3 covariance matrices. And notice there is a chunk of code where you define the data. There is another chunk of code where you define the parameters. And then it follows a chunk of code for the transform parameters where you decompose the covariance matrices. And then you specify the linking model. And at the bottom in the second column, you see the theta I. So those are eventually the parameters of interest. And then you have a chunk where you define your model and all the prior distributions for the different parameters. And finally, you can have a piece of code for defining the log likelihood. We use that eventually for model comparison. So in the next slide, you'll notice this is one way you can specify a model using the LKJ type 2 prior. And I'm not going to go through this, but the slides will be available after the talk. And in the third slide, you'll see the next slide. You'll see the model specification, again, an RStan model specification for this model with inverse Wishart distribution for the 3 covariance matrices. Next slide, please. And after fitting all the models, we noticed that the Markov chain Monte Carlo diagnostics, all the results look good. So for example, the MC effective sample sizes were greater than 5% of the total sample size, the 4,500 samples that we use for inference. The MC standard error was small relative to posterior standard deviation. The R hat factors were less than 1.1, so mixing and convergence look good for all the models. And also the autocorrelation decreased with an increase in lag, so, and generally was less than 10%. So based on these results, we weren't yet convinced what prior distribution to adopt for the covariance matrices. So we conducted a sensitivity analysis study. So in the next slide, I'm showing some results for the sensitivity analysis, so we concluded that the model is sensitive to the choice of prior, specifically LKJ versus inverse Wishart. And the model is not sensitive to the choice of LKJ type prior, the type 1 and type 2. And interestingly, we also found that the model was sensitive to the specification of the inverse Wishart prior. And the inverse Wishart prior has the degrees of freedom parameter, which is fixed to be 2, and it has the scaling matrix S, for which we looked into an informative choice or a non-informative choice. And we noticed that the models were sensitive to that. And also we fitted this model using initial values for all the latent parameters at the county, state, and division versus not specifying initial values. And again, we noticed that the model was sensitive to that choice as well. And the posterior means for the regression coefficients, the beta coefficients in the model, and also the posterior means for the county level proportions, the theta parameters that are eventually of interest, were comparable across all the model specifications. So the sensitivity came in the posterior variances. Specifically, we noticed that the county level posterior variances under the models with the inverse Wishart priors are larger than the posterior variances under the models with the LKJ type priors. And this finding is consistent with two papers in the literature that I mentioned before. So to show you some example results, here I have 4 plots. In the first column, I'm illustrating proportions at or below level 1 in the first row, and proportions at or above level 3 in the second row. So in the first column, we look at comparison of county level posterior means for these 2 proportions with 2 model specifications. On the x-axis, we have a model specified using the LKJ type 1 prior. And on the y-axis, we have the model specified using an inverse Wishart, using the LKJ type 2 prior, where we decompose the correlation matrix into the Cholesky factors. And notice that the posterior means are essentially the same. In the second column, however, we're looking at the posterior standard deviations for the 2 proportions. And again, the same x-axis and y-axis. And notice that also the posterior standard deviations are are very similar. They're not the same, but they are very close. In the next slide, I'm illustrating posterior means and posterior standard deviations, again, for the two proportions, first row and second row respectively. However, using two different types of priors. On the x-axis, again, we have posterior summaries based on the model with the LKJ type 1 prior, the final prior that we adopted for the models. And on the y-axis, we have posterior summaries using a model that using an inverse Wishart distribution with an informative S, and also providing initial values for the 3 latent parameters. Again, we notice that the posterior means are comparable, and we start seeing the differences in the posterior standard deviation, specifically larger values for the models with the inverse Wishart distribution compared to the LKJ. And in the next slide, we can take a look at posterior summaries based on models using inverse Wishart distribution with different specifications. On the x-axis, we have models using inverse Wishart distribution using an informative scaling matrix X, as well as on the y-axis. The difference comes in whether or not we specified initial values for C, D, and V. And notice that the posterior standard deviations change based on the specification as well. In the next slide, we're comparing posterior summaries based on models, again, using inverse Wishart distributions, this time using a scale matrix that is vague, for example, identity matrix multiplied by some large factor versus an informative S matrix. And again, we notice that the posterior standard deviations are different for these two specifications. So consistent to the result that I mentioned before, that the models seem to be sensitive with inverse Wishart prior distribution specifications, even under the different specifications of these priors. Next slide, please. So to take a look at the posterior summaries for the coefficients of these matrices, we can understand why this is happening. Why are we seeing that under the inverse Wishart distribution, the models seem to be sensitive? So here we're reporting posterior summaries for the 3 components of the sigma C matrix. So that's the covariance matrix for the county level latent effects, and sigma V matrix, the covariance matrix for the state level effects, and sigma D matrix, the covariance matrix for the division level latent effects. Posterior means posterior standard deviations under the different prior specifications that we investigated. And we compare these summaries against the posterior means and of the sampling variance sigma, so that's denoted at the bottom. So what we notice is that under the LKJ, these 3 variance covariance matrices, the sigma C, sigma V, and sigma D, specifically the diagonal elements, so the estimated variances, are much smaller than the sampling variances where we started with. And this makes sense because our covariates had very good predictive power, so we did not expect that the latent effects to explain much. There wasn't much variability left for these 3 latent effects to explain. So we were expecting to have smaller variances for this sigma C, sigma V, and sigma D, the entries in these matrices. Compared to the inverse Wishart, the last 3 sets of columns under the different specifications, notice that under the inverse Wishart, the variance components are much larger. The posterior means, for example, are much larger, and they are not so small compared to the sampling variances as we expected. So what happened, and also notice that under specifying or not initial values, we do see a difference in the posterior means versus, and we do not see that large of a difference when we look at different S matrices, the scaling matrices for the inverse Wishart distribution. But we do see that the results are different under that specification versus the LKJ. So as I said, this is expected because of the good predictive power of the covariates. We are indeed in the same set up as the two papers that I mentioned before. We have a small number of counties that we're working with, only 184. And we're trying to borrow information from that nested level. There are 44 states and 9 census divisions, so not too much there. And one final thought would be that the model sensitivity analysis may reveal more. As you saw, the MCMC diagnostics were fine for all the models. However, in the sensitivity analysis, we found some more. And it helped us make a choice for the final prior to for the models. And I'm referring to Simpson et al. 2017 as another paper on approaches on how to construct priors, and they specifically talk about complexity, penalized complexity priors, and they go through steps by steps on how to construct priors for complex hierarchical models. Next slide should be a slide with some selected references. And finally, my last slide with my contact information on the next slide. Thank you so much.
Thank you. That's a lot. We have a question from the chat box from
Great.
Nathan Cruz about the survey instrument. Is it the same across all 3 years in question? And how is it administered? Would the respondent have to be literate to complete the survey?
Those are very good questions. There was a large team of people working on this, Nathan. So I don't know the answer to it. I know that right now we're conducting another cycle of the survey, and the assessment, the assessment is the same, but comparing across the 3 years, I'm going to have to talk to my colleagues and find the answer to that and get back to you. Thank you for the question.
Thank you very much.
Thank you, Peter.
Okay, our next speaker is Talini Mahanama. I will step aside. You ready to speak?
Yes, I am.
Excellent.
Hello, everyone. I am Tiruni Mahanama from Texas Tech University. It is my pleasure to present my recent research findings to you. This is part of my research under the supervision of Professor Dmitry Volchenko. In this work, we are going to address 3 problems in tornado data analysis. Next slide, please. First of all, let's study about tornadoes in the United States. Tornadoes typically occur in late spring and occasionally the early fall. The US sustains about 1,300 tornadoes annually. Please have a look at the total property losses reported in the states of United States. It is in figure A. For our study, we got this data from National Oceanic and Atmospheric Administration. As you can see, tornadoes hit the areas like, I'm sorry, I cannot show you with the cursor. Texas, Oklahoma, Kansas, Iowa, Missouri, and Nebraska. Then these states have a significantly high frequency in terms of tornadoes. So this region is known as Tornado Alley. In figure B, you can see the number of tornadoes reported in the Tornado Alley. Around 4,000 tornadoes hit Texas since 1950. Tornadoes cause significantly high economic impacts in the United States. Thus, insurance policies should be modified for sustainability. Next slide, please. In our study, we are going to analyze data using 3 methods. First, we classify tornado events using property losses. As a result, we propose a new scale for tornadoes. Second, we determine the dependence between tornado variables. And finally, we predict future property losses for the United States. According to our findings, the volumes of property losses would amount up to $8 billion in 2025. Next slide, please. Let's see more details on tornado data. First, we adjust property losses for US dollars in 2019. And in this figure, you can see the path of a tornado. You can see the path length, which is marked with a line, then the path width is also marked there. So whenever appropriate, we approximate the area affected by the tornado as a product of these two measures. Now let's see how to classify tornadoes. Currently the US use Enhanced Fujita scale. Simply we call it as EF scale. This scale classifies tornadoes based on their intensities. Moreover, they measure the intensity using wind speed estimates and qualitative measures on the related damages. Here you can see the EF scale on increasing degree of damage. Later we are going to introduce a new scale for tornadoes. For that, we are going to use the three variables we mentioned above. That means the property losses, length, and width. Next slide, please. Now let's see how we are going to classify tornadoes. Here you can see the tornado data in a matrix. These columns represent the tornado variables we discussed earlier. So we can do a multivariate analysis. Usually we use principal component analysis to find the hidden structure of the multivariate data. Please notice in this matrix we can have only positive values. That means no non-negative values. That means non-negative values. Therefore, the interpretation of principal components are going to be vague for our data. For example, negative property losses are meaningless. Moreover, we found these variables follow non-Gaussian distributions. So we forego principal component analysis to get better results for tornado classification. Then we chose non-negative matrix factorization. I will show it as NMF. NMF is a recommended method for non-negative data. Moreover, it outclasses PCA in terms of strongly correlated non-Gaussian data. In non-negative matrix factorization, we approximate the data matrix as a product of two non-negative data matrices. Here you will see them as W and H. We call them as factor matrices. They represent latent and salient components of the dataset. In particular, we approximate each variable as a linear combination of the factor matrices. Then lastly, you can see those linear combinations, and the collection of these three variables gives us the tornado data matrix. Next slide, please. We choose the multiplicative update algorithm based on its performance. In this figure, we provide a visual representation of NMF results. The vectors are the tornado variables, and you will see small points. Those represent tornado events. And these vectors or points are on the two-dimensional plane constructed by the two salient components of the non-negative matrix factorization. Furthermore, we have colored the tornado events, that means the points, according to their intensity. You will see the intensity scale on the legend. That is EF scale. And this illustrates a poor classification with the colors of the intensity, because none of the tornado variables, that means loss, width, length, are used to construct the EF scale. Also, some severe tornadoes show low property losses, while some mild tornadoes show high property losses. This shows property losses do not exhibit a direct relationship with the intensity. Also, please notice the clusters of points. There are 8 clusters, main 8 clusters, are orthogonal to the loss vector. Next slide, please. Then earlier we observed a conspicuous classification in terms of property losses. Therefore, we propose a novel classification accounting for property losses. We call it as tornado property loss scale, TPL scale. A tornado with the event which has TPL scale equal to 50 indicates that the tornado has 100,000 times, the loss of the tornado is 100,000 times higher than the minimal loss, which is 10. And you will see a segment in this figure, which is magnified. Here you will see the section of TPL scale greater than 60. According to their results, there are like 2.5 chance a tornado will occur, causing over $10 million in damages. Correspondingly, we can infer the TPL scale when the property loss of a tornado is given. Next slide, please. Now we are going to measure the dependence between tornado variables. Here we consider the area of a tornado and its property loss. In figure 1, in the left side figure, you can see the tornado variables are not linearly related. Also, we found the two variables, area and loss, follow non-Gaussian distributions. Now we need to find the dependence between these two variables. Here we cannot use the Pearson linear correlation coefficient because these data are nonlinear and they follow non-Gaussian distributions. On the other hand, we can measure the nonlinear dependence using some other measures. For example, Kendall's tau and Spearman's rho. However, they fail to explain the dependence structure of extreme events. Therefore, we use a coupled approach to determine the nonlinear dependence between property losses and area. Let me define what is a copula. Here we are going to use a bivariate copula because we have two variables. A bivariate copula is a function of two variables which couples the joint cumulative distribution function to the marginal CDFs. That is what you will see on the formula. It couples the joint CDFs to its marginal CDFs. The copula function contains the information about the dependent structure of the two variables. Hence, we can use copula approach to investigate the dependence of these two variables. For that, the marginal distribution should be properly defined. Therefore, first we have to identify the marginal distributions of the area and losses. Then after that, we are going to determine a proper copula function. Then we can estimate the copula parameter, which is given in theta, using the maximum likelihood method. Here this theta provides a nonlinear dependence between area and losses. Next slide, please. First, we investigate the sampling distributions of loss and area. We tried with several distributions like Weibull, Gamma, NIG, like that. Then we estimate their parameters using maximum likelihood method. To find the best fit, we use a goodness of fit called Anderson-Darling test. Then we found those two variables follow gamma distributions, and you will see the shape and rate parameters of them. Then we are going to find a copula function. There are no common principles to find the optimal copula function for a data set. So we tried to find one using trial and error method. We tried Gaussian and T copula among elliptical copulas, and Gumbel, Frank, and Clayton copula among Archimedean copulas. Then based on their performance and goodness of fit, we chose Gaussian copula for our study. The first two figures give you the joint densities of the two variables that we got from the copula approach. Then after that, you will see a comparison of observed and simulated data, and you can see they seem to be approximately similar. Then finally, we have given the dependence structure of the two variables, which we give as theta, that means a copula parameter. Next slide, please. When we calculate the copula parameters for the annual tornado data for each state in Tornado Alley. According to this figure, you can see there is no monotonicity in copula parameters over the years and states. Therefore, the correlation between tornado variables vary with time and geographical location. So here we cannot capture the tendency of property losses using this copula approach. Therefore, we are going to use a better approach to find the tendency of property losses in time series analysis. Next slide, please. As we have already seen, the property losses will depend on time, geographic location, and seasonal effects. So when we are going to predict, we should capture these things from our model. That means the model should be able to have very good memory, long and short memory, to capture these patterns. Therefore, we develop a long short-term memory neural network. Here we use an LSTM network composed of an input layer and an output layer. Then we set one neuron for each. Here, these are for the input data, and these are the predictions. In between them, there is a LSTM layer. We set 500 neurons for that. Also, we got that number based on trial and error. This LSTM determines what information to store in the memory and how long to store it and when to read it out. It is controlled by the multiplicative units given in this figure. Input controls how much data to read, and the forget controls how much they should have to proceed. Then in output, we will get the predictions. This is an iterative process. So here I have shown you only one LSTM block. There are several of them. So in each step, it updates with the memory of the previous state. Likewise, we will get a better results using this long short-term memory neural networks. Next slide, please. We apply an LSTM for predicting future monthly losses. In figure A, you will see the predictions for monthly losses in 2019. Then also, that is what we did earlier. Then in 2019, at the end of 2019, we compared our results with the observed data. And here you can see there seems to be approximately the same, except for the months September and October. Those results were extremely high results, unexpected results. And furthermore, we predict the losses for the next 5 years. Then we got the so-called tornado season, which is from March to June. You will see the pattern there in figure B. And the volume of losses would amount up to $8 billion by 2025. Next slide, please. Now I am going to summarize our findings. In the traditional scale for the tornadoes, they use wind speed and a qualitative measure of property damages. However, The property loss caused by a tornado depends on the value of the real estate. For example, the property loss of a tornado in an urban area might be significantly high, even if the tornado has a low EF scale. Therefore, we introduce a new tornado property loss scale considering the property losses. After that, we investigate the dependent structure of tornado data using a bivariate Gaussian Copil approach. However, the calculated dependent structure between the two variables vary with time and the location. Therefore, we move to a method in time series, that is long short-term memory neural networks. Therefore, finally, we predicted the future monthly property losses due to the tornadoes using a LSTM network. Based on our findings, the volume of property losses would amount up to $8 billion in next 5 years. That's the end of my presentation, and thank you. Any questions?
Thank you very much. I don't see a question yet. We've come to the end of our time. Thanks to all our presenters for really sophisticated and insightful findings and presentations. We have just 5 minutes and then we come back at 3:10 for more presentations.